Welcome to our lecture on directional derivatives and the gradient vector. In multivariable calculus, we often need to understand how a function changes in different directions. Today, we'll cover two key concepts, directional derivatives and the gradient vector, which are powerful tools for analyzing the behavior of multivariable functions. Let's start by visualizing what a directional derivative actually means. Imagine we have a function f of x and y, which represents a surface in three-dimensional space. Let's say we're standing at a specific point on this surface. From this point, we could move in any direction, east, west, north, south, or any combination. The directional derivative tells us the slope of the surface as we move in a specific direction. Now, let's define the directional derivative mathematically. The directional derivative of function f at point A in the direction of a unit vector u is defined as the limit of the difference quotient as h approaches 0. Intuitively, it measures how quickly the function f changes when moving a tiny amount in the direction of vector u. When u is a unit vector, there's a key formula connecting the directional derivative to the gradient. d sub u of f at point A equals the dot product of the gradient of f at A with the unit vector u. This equals the magnitude of the gradient times the cosine of the angle between the gradient and the direction vector. Let's now define the gradient vector. For a differentiable function f, its gradient at point A is the vector of partial derivatives. The gradient has two important properties. First, its magnitude is the maximum rate of increase of the function at that point. Second, it points in the direction of steepest descent. Additionally, the gradient is perpendicular to the level curves of the function. Let's visualize this for our function f of x, y equals x squared plus y squared. Now, let's understand how directional derivatives change based on direction. Recall our formula. The directional derivative equals the dot product of the gradient and the unit direction vector. When the direction aligns perfectly with the gradient, we get the maximum value. When the direction is perpendicular to the gradient, the directional derivative is 0. And when the direction is opposite to the gradient, we get the minimum negative value. Let's visualize the directional derivative in all directions from our point at 1, 1. Let's work through an example in 2 dimensions. We'll compute the directional derivative of f of x. Y equals x squared y plus 3y at the point 1, 2 in the direction of the vector v equals 3, 4. Step 1. Compute the partial derivatives. The partial derivative with respect to x is 2xy. The partial derivative with respect to y is x squared plus 3. At the point 1, 2, the partial derivatives evaluate to f sub x at 1, 2 equals 2 times 1 times 2, which is 4. F sub y at 1, 2 equals 1 squared plus 3, which is 4. So the gradient vector is 4, 4. Step 2. Normalize the direction vector. The magnitude of v is the square root of 3 squared plus 4 squared, which equals 5. So the unit vector u is v divided by its magnitude, which gives us 3/5, 4/5. Step 3. Calculate the directional derivative using the dot product. The directional derivative is the dot product of the gradient 4, 4, and the unit vector 3/5, 4/5. This gives us 4 times 3/5 plus 4 times 4/5, which equals 12/5 plus 16/5, or 28/5, which is 5.6. So the rate of change of f at 1, 2 in the direction of vector 3, 4 is 5.6. Let's work through another example, this time in 3 dimensions. We'll find the directional derivative of g of x. Y z equals x times e to the yz minus z squared at the point 0, 0, 1 in the direction of the vector w equals 1, 1, 2. Step 1. Compute the partial derivatives. The partial derivative with respect to x is e to the yz. The partial derivative with respect to y is xz times e to the yz. The partial derivative with respect to z is xy times e to the yz minus 2z. Evaluating at the point 0, 0, 1 g sub x equals e to the 0, which is 1. G sub y equals 0 times 1 times e to the 0, which is 0. G sub z equals 0 times e to the 0 minus 2 times 1, which is minus 2. So the gradient at 0, 0, 1 is 1, 0, minus 2. Step 2. Normalize the direction vector. The magnitude of west is the square root of 1 squared plus minus 1 squared plus 2 squared, which equals the square root of 6. So the unit vector is 1, minus 1, 2. divided by the square root of 6. Step 3. Calculate the directional derivative using the dot product. The directional derivative is the dot product of the gradient 1, 0, minus 2, and the unit vector. This gives us 1 times 1 plus 0 times minus 1 plus minus 2 times 2, all divided by the square root of 6. That equals 1 to 4 divided by the square root of 6, which is minus 3 divided by the square root of 6, or negative 3 times the square root of 6 divided by 6, which is negative square root of 6 divided by 2. So the directional derivative at 0, 0, 1 in the direction of 1, 1, 2 is negative square root of 6 divided by 2. Since this is negative, it means the function decreases when moving in the direction of vector w from the point 0, 0, 1. Let's summarize what we've learned about directional derivatives and the gradient. The directional derivative measures the rate of change of a function in a specific direction. It can be calculated using the dot product of the gradient and the unit direction vector. The gradient vector points in the direction of steepest increase, and its magnitude gives the maximum rate of change. The gradient is perpendicular to level curves or level surfaces. These concepts have important applications in optimization, where we want to find the direction of steepest ascent or descent, and in physics, where gradients appear in many fundamental equations. To calculate a directional derivative, follow these steps. 1. Compute the gradient by finding the partial derivatives. 2. Evaluate the gradient at the point of interest. 3. Normalize your direction vector. 4. Take the dot product of the gradient and the unit direction vector. Thank you for watching. And I hope this helps you understand directional derivatives and gradients better.